Hi, welcome to Mathematics with Tom. I'm Tom, and today we're going to solve the system of differential equations with complex eigenvalues and complex eigenvectors. So I've written it down here. Here's our system of differential equations. We have y prime equals the matrix A, which, well, just to help clarify, that's the matrix A times the vector y. And our matrix A by columns is minus 2, minus 1. And 1 minus 2. Here we go. So it starts out the same. The first thing we need to do is find our eigenvalues. So let's do that. Find lambdas. That's what we're going to do first. Well, remember, we know that this gives the characteristic equation of lambda squared minus the trace. Well, in this case, the trace is minus 4, or minus 2, minus 2, so minus 4 times lambda, plus the determinant, and the determinant in this case is going to be a 4 minus negative 1, and this is going to give me 0. To clean up, the characteristic polynomial is lambda squared plus 4 lambda plus 5 equals 0. And I wish that would factor, but it doesn't. So let's use our quadratic formula. So we have that lambda is equal to minus 4, I'll write this way, minus 4 plus or minus the square root, and then we take b squared, so that's 16, minus 4 times the 5, so that's a minus 20. I'm going to divide that by a 2, so we can say then that lambda is, let's see, minus 4 plus or minus, well, 16, oh, not 16 squared. Goodness, you guys should have said something. There we go. 4 squared is 16. That looks better. Okay, and then let's see. So 16 minus 20 is negative 4. Square root of negative 4 is 2i. So 2i. Divide that by 2. Let's just factor a 2 and simplify. So lambda is minus 2 plus I and minus 2 minus I. Now, this takes a little bit more doing, but the process is the same. So let's write this out. So the first thing we're going to deal with here is A minus our lambda, which is minus 2 plus I times I. And we are going to solve when that is times our first eigenvector equals 0. Oops. Well, I'll put that here in a minute. Well, a minus 2i, that's going to be a negative 2 plus 2. That's 0. So this is going to be a minus I. And then a 1. And then I'm going to have a negative 1. Then we're going to have another negative 2 minus the eigenvalue, so this is going to be a minus I as well. Times V1 equals 0. Now remember, you always should check, can I multiply the first column by something to get the second column? And it looks like if I multiply the first column by I, maybe? I, so minus I times I, oh, that'd be 1. There you go. And then I, yes, there it is. So we did this correctly. We have dependent columns, or you can think of them as dependent rows as well. Now, so when we solve this, we know that if we can row reduce, and this second row will become a 0. So what we're really looking at is this gives me this relationship that minus I, V1 is equal to minus V2. I'm going to simplify that as I times V1 is equal to V2. And so I'm going to say that my eigenvector, V1, is, let's just use that V1 is 1, so that would make V2. That would make V2I. Okay, so I'm just going to choose that. This looks like the best choice. All right, let's do this again. So now let's take a minus our second let me record this. I should have. This is for lambda 2, which is minus 2 minus I. So let's take a minus minus 2 minus I times the identity I times the second eigenvector. Well, what this is going to do is give me this matrix of I, 1, minus 1, and I. It's just going to change that negative I to a positive I from our previous problem. V2 equals the 0 vector. It's the 0 vector. And notice that if I multiply the first line by I, or the first column by I, then I get, let's see, I times I, no, minus I. I have to multiply by minus I. Because then, did I do that right? Let's see. Yeah, I don't want to make a mistake here. Let's just see about that. If I multiply the first one by a minus I, yeah, there you go, minus I. So they're dependent columns. Well, good. Now notice this first row. This first row says that I times V1 is equal to minus V2. So I'm going to let my second eigenvector, I'm going to pick V1 as 1, and so V2 is minus I. And there we have it. Now you think, oh, we might be done. Well, let's just check and see. So let's write our solution. Our solution now is y equals, this is our null solution, but since q is 0, then, or our source term is 0, this is also our complete solution. Or in general, we just write y. So that means I have some coefficient, c1, times my first eigenvector, 1i, and times e to the minus 2 plus I times t plus c2 times my second eigenvector, which is 1 minus I times e to the minus 2 minus I times t. Okay. It's this that we're, let's see, yes. Oh, also, I'm going to go add this here. We're going to set y of 0 equal to the vector 6, 2. So we're going to even deal with some initial conditions here in a moment. Let's see, is that what I want to do now? Now, let's use our initial conditions to find C1 and C2. So I'm going to just plug this in. So this says that y of 0 equals, this becomes a C1 times 1i, and then e to the 0 is just 1 plus C2 times 1 minus I, and this has to equal, well, what does this have to equal? This has to equal my initial condition of 6, 2. Now look at what just happened. This left-hand side it's a scalar times a vector plus a scalar times a vector. This is really solving the matrix equation of 1i, 1 minus I, times C1, C2 equals my initial condition 6, 2. So what does this tell me? What does this tell me? This really is, what this is saying is we called this earlier, the matrix of eigenvectors is V. So this is really just V times a matrix of scalars equals our initial condition vector. So we can just find our initial conditions by solving VC equals y of 0. And we're going to do that, and we're going to do that on the next page. Wow, I have to admit this is a little bit rough, but let's just be consistent with our notation. I'm going to start out with this. I'll just rewrite it for clarity. 1i, 1 minus I. And let's just write the augmented matrix 6, 2. So now that I'm going to take row 2 minus I times row 1. Well, let's see, what's that going to produce? The first row is unchanged, so 1, 1, 6. Then I minus I is 0. Minus I minus another I is minus 2I. And then 2 minus 6I. Whoa, okay, so 2 minus 6I. There's my augmented matrix. And then you could keep going, but I think it might be just easy enough to use back substitution, because really this says that minus 2I times C2 is 2 minus 6I. I'm going to divide both sides by, all right, so C2 is equal to 2 minus 6I over minus 2I. So this is equal to, let's break this up. This is 2 over minus 2I and minus 6I over minus 2I. So this is going to be a minus 1 over I plus 3. And then let's multiply this minus 1 over I by a minus I. And so that's going to just give me, a 3 plus I, because I times minus I is 1, and minus I times minus 1 is positive I. There we go. That's our first, that's C2. And now we can find C1. So then, what do we have? We have that C1. So 1 times C1 plus C2. Well, C2 is 3 plus I. This has to equal 6. So let's just clean this up. Is that right? 6, yep. So, C1 equals 6 minus 3. That's going to be a 3 minus I. And there we have it. So now, wow, we can even write this, our formula, our solution like this. Now we can say that y is C1. So that's 3 minus I. 3 minus I times the eigenvector. We said that was 1I. E to the minus 2 plus I t plus, and what do we have? Then C2 is 3 plus I, 3 plus I times the eigenvector of 1 minus I times e to the minus 2 minus I t. Now let's just do a little bit of thinking about that. E to the minus 2 minus I t. Remember, so I'm going to just do a note down here. So e to the e raised to the minus 2, we'll do both, we'll work on the first one, plus I t. Remember, if I distributed the t, this is e to the minus 2t plus I t. Well, that's the same as e to the minus 2t e to the it. Well, that's even better, because that is e to the minus 2t times, by Euler's identity, that's cosine, t plus I sine of t. And you can do the same with e to the minus 2 minus I times t. So let's write that out, because that's e to the minus 2 minus I t. So that is e to the minus 2t minus it. But that is e to the minus 2t times cosine of t minus I sine of t. Remember, that happens because sine is an odd function. All right, well, let's just, now notice this. Notice that both of these terms have in common to them, they have this e to the minus 2t. So I'm going to just factor that out and deal with my C1 and my C2 and my V1 and V2, my eigenvectors and my constants. So let's rewrite this as, probably give yourself plenty of space. So y equals e raised to the minus 2t times, okay, here we go. So this is going to be the eigenvector of 3 minus I, and then 3i. I'm just distributing my scalar multiplication, and then an I times a negative I is, just drew a blank there. Oh yeah, 3i, there we go. That's 1, so plus 1. Plus 1 times, but now, so it's that, all of that is being multiplied by e to the it. Well, e to the it is cosine of t plus I sine of t. That's my first eigenvector times the complex exponential. And if we do this again, now we're going to have a 3 plus I. So I just went 3 plus I times 1. And now 3 plus I times the negative 1, that's going to give me a minus 3i plus 1 times, this is e to the minus it. Well, that's cosine of t. Remember, this is scalar multiplication, so it has to get both components of the vector. Minus I sine t cosine of t minus I sine t. Okay. Oh, yeah, and then e times e to the minus t, which is really being multiplied by everything like that. There we go. So I'm going to copy this. We're going to have to go to another page, I think. Now, let's see. So now I can write this as y equals e to the minus 2t times. Okay, now I'm going to start distributing. So we'll work on the first entire row. So this is going to be a 3 cosine of t, 3 cosine of t plus 3 times I sine of t. And now I'm going to distribute the minus I, so that's going to be a minus I cosine of t, and then a minus I times an I, that's plus 1 sine of t. Then I keep going. Now I have plus 3 cosine of t minus 3i sine of t. And then plus, that's going to be a plus 1 sine of t. Okay, there we go. I think that'll fit in there. Now the second row. So this is a 3i cosine of t. And then, oh, that's going to be a minus 3 sine of t. Then I distribute again, plus a cosine of t. And then plus an I sine t, plus I sine of t. And now we're into this next, we're into our last component. So this is going to be a minus 3i cosine of t plus 3i squared. Well, that's really going to be minus 3 sine t. There we go. That's looking better. Now, plus cosine of t, plus the cosine of t. And then our last term is going to be minus I sine of t. Just fits. Look at that. Okay, now let's clean this up. So now I can write this as y equals e to the minus 2t times, and let's see what we've got. So I'm going to just start looking for some like terms that might cancel in here. I think there are some. Here's a 3i sine of t, and I have a minus 3i sine of t. And let's see, I have a minus I cosine of t. Ooh, maybe that one's in there, huh? I think I made a mistake somewhere. You guys should have said something. Oh, I totally forgot a term. That's why. Goodness gracious, jeez. So look at this. 1, 2, 3, 4. So right here, there's 1, 2. I forgot right here. I forgot plus I cosine of t. There we go. I should have drawn my arrows. Maybe I would have seen that more readily. So there's a I cosine of t. And if I add up what I have left now, it looks like I have 6 cosine of t, 6 cosine of t plus 2 sine of t. And let's try this again. Let's grab another color and let's see. 3i cosine of t minus 3i cosine of t. There's an I sine of t minus an I sine of t. So if I just write what I have left, it looks like I have minus 6 sine of t and 2 cosine of t. And there we go. And that is our solution to our differential equation when we have complex eigenvalues and eigenvectors. I hope that helps, and thanks for watching.